Okay, welcome back to Chapter 4. This is Section 4.2. I think in the book this is called Prime Factorizations and Reducing to Lowest Terms. I'm calling it GCFs and Reducing to Lowest Terms. These names are somewhat arbitrary. So we're still in the fraction section. What we're trying to do is get to the point where we could take any fraction and obviously reduce it to lowest terms. Part of doing that, we need to talk just sort of generally about numbers first. Reducing to lowest terms is going to involve sort of taking numbers apart into their individual factors, and then sort of dividing away any common factors. In particular, the GCF, which is what's known as the greatest common factor. So reducing a fraction to lowest terms is going to involve sort of finding and dividing away the greatest common factor. But as always, we sort of need to learn to crawl before we can walk and run, so we need to sort of build up to this a little bit. The first thing is we just need to sort of talk generally about numbers, and in particular the idea of a prime number versus a composite number. So prime and composite numbers. So I sort of use the example in class of saying this is sort of similar to sort of chemistry, where you have the periodic table that you have your sort of basic elements that can't be broken down anymore, right? Hydrogen, carbon, helium, these kind of things, and then from that you can make different things. So like water, for example, is H2O, so two hydrogens and sort of one oxygen. It sort of has this unique kind of formula based on these elements to sort of get this new thing. Numbers work in the exact same way. So our prime numbers are our sort of foundational numbers. They're sort of what we use to build the other numbers, and the composite numbers are the numbers we sort of build with the primes. So our kind of definition here is going to be, so prime number is a number whose only factors are 1 and itself. A factor is a number that will sort of divide evenly into another number, right? So like 3 divides evenly into 12, so 3 is a factor of 12, right? 2 divides evenly into any even number, right? So 2 is a factor of all of the even numbers. 5 divides evenly into 50, so 5 is a factor of 50. So a prime is a number that won't break down. It won't break down into sort of smaller values via sort of division, right? So this would include numbers like not 1 itself, so technically we'll sort of start them at 2, but numbers like 2, 3, 4, right? So any even number bigger than 2 is divisible by 2, so it's not going to be prime, but you could then of course jump to sort of 5 or 7, right? So kind of by necessity, all of our primes will be odd numbers once we get sort of over 2. 9 is not going to be prime, right, because 9 is divisible by 3. But you get to something like 11 or 13. 15 is divisible by 3 and 5. But then 17 and 19 would be prime. 21 is divisible by 3 and 7. But then 23 is not divisible by anything, right? 25, 27, have factors that are not just one of themselves, but you could then do 29, 31, and so on and so forth. You can actually sort of get prime numbers up literally as high as you want to go. In sort of upper level math, it's possible to sort of do proofs and sort of demonstrate the cleverness and sort of reasoning that you can sort of always build a bigger prime number. You can always get, no matter how high you get, you can sort of always find a new prime number. In any event, to a certain extent, they sort of get fewer and sort of farther between as we sort of go up. A composite number then is sort of any number that has some other factors besides 1 in itself. So any number that has a factor larger than 1. So any number with a factor well, larger than 1, and I guess we should say, right, other than itself. Right, so this is things like 2, 4, 6, 8. Again, any of the evens, things like, 9 and 15, 27, right, 35. All of these numbers, you can divide something into them besides 1 in itself, and so that's going to make it a composite number, right? It's made of other numbers, which is what it means to be composite. So if we have composite numbers, right, what that means is we can actually break them down into their prime factors. So composite numbers can be broken down into their prime factors. And this gives us sort of a unique way of actually sort of representing these numbers. It's not just enough to say you can break them down into their prime factors. When you do that, you get a unique sort of formula of numbers in the same way, right, that sort of water is uniquely H2O, 2 hydrogens and oxygen. Numbers, right, any sort of composite number is going to be uniquely made of other numbers. And so this is what we call the prime factorization. So let's just sort of run a couple of these. The best way to do this, I think the most effective and easiest way, is to use what I would call what I and others have called a factor tree. So for example, let's take something like 36. Let's get this little hair out of here. So the idea with a factor tree is that you take a number, right, some sort of composite number, and what you do is you sort of visually represent the factoring by splitting it apart and into sort of any of its different factors. So for example, 36 would be a product of lots of different things, but let's just take, for instance, 3 and 12, right? So 3 times 12 is 36. You could also use, right, 4 and 9. You could do like 2 and 18. You could do 6 and 6. 36 has actually a surprisingly large number of possibilities here. The good news is that no matter how we start this, no matter how we start the prime factorization, we're just going to keep sort of breaking it down until we can't anymore. And so going through that process, we're always going to end up with the same values. So the idea is that you sort of use this factor tree sort of visualization, you break it apart, and then at the next level, if you can break it again into smaller factors, you do. If you can't, so for example, 3 won't break down any further because it's a prime. So 3 is the end of that branch. 12, of course, we could break down a little more. You could call 12 3 times 4. This gets us another 3, which is a prime. So we're kind of closing in on sort of getting this narrowed down. And then our last split, of course, 4 would be 2 times 2. And so what happens here is 36 is really made up of these sort of smaller individual primes. It's really made of, in this case, 2 times 2 and 3 times 3, right? It's made of 2 2s and 2 3s. So 2 times 2 times 3 times 3 gets us back to 36. This would be sort of 4 times 9 would be 36. We can sort of group these and multiply sort of however we'd like to. What we can do from here is we can sort of take it and we can be a little bit more efficient with how we write it. We can sort of write it in exponential form, right? So for example, 2 times 2 would be 2 squared, 3 times 3 would be 3 squared. So I'll kind of write our final versions of this here in exponential form, just for efficiency's sakes. So that's exponential. Let's take another example. I'll just sort of squeeze it in over here. What number should we do? This is a good question. How about let's do something like 54, maybe. These are sort of just examples off the top of my head. Again, the nice thing about this is it doesn't particularly matter When you sort of get one of these numbers, you can kind of start with small factors. So 54 is even. So you could certainly start by just sort of breaking it by 2, would be like 2 times 27. Or you could maybe sort of aim a little bit more for factors that are kind of closer together, aim for something kind of in the middle. So I'll actually do that here. And so 54 would be 9 times 6, for example. And then both of those we can break down further, right? 9 would be 3 times 3, and then 6 would be 2 times 3. So we get a little bit, just visually, a little different sort of version of the tree. It's kind of interesting in some sense, depending on how you break it down. You might get trees like this one that's sort of kind of leaned to the right. This one is a little bit more balanced, and we're sort of breaking and then sort of breaking each of them again. Again, how we do this is it really sort of just varies from sort of problem to problem. In any event, 2s and 3s obviously are all prime numbers. So we'll sort of box those, the ends of our branches. And we have, in this case, 54 is made of 1, 2, and then it looks like 3 3s, sort of all in a row. So written in exponential form, we would call this 2 times 3 cubed. So our prime factorizations, right, are sort of made of these prime factors. And every number has a unique version of this. This is actually sort of in upper level mathematics and sort of number theory. This is kind of a foundational concept, the idea that you can kind of uniquely write any number as a product of its primes. That's not exactly what we're doing right now, but if you want to nerd out sometime and talk about math, that's the kind of thing you can look into. In any event, we'll sort of keep this going in the next video.